Hi, welcome back to our topic electrochemistry. Last time, we discussed the first branch of electrochemistry, which is the voltaic cell. We were able to compute the potential involved at the standard condition and in the non-standard condition. This time, we'll talk about the other branch of electrochemistry where the chemical reaction is produced by electricity, which is electrolysis. This episode on electrolysis will involve two parts. The first part is identifying the electrode product, and the second part is a quantitative computation of the reaction. The second part is the quantitative computation of the reaction that involved or produced at the respective electrode of an electrolytic cell. To begin with, let us define electrolysis. The process of electrolysis takes place in an electrolytic cell. So we can represent the electrolytic cell by this schematic diagram where the two electrodes are within the same solution. Okay, so as a direct current is passed through a solution of an electrolyte, the anion moves towards the anode where they give up their electron. And the electrons move to a metallic conductor through a generator of the electric current to the cathode, where the cation are discharged by taking up this electron. So in this case, the anion X here will give up electron to undergo oxidation. Remember, we have discussed in the first part of electrochemistry, for both electrolytic cell and voltaic cell, the oxidation reaction must take place at the anode and reduction reaction must take place at the cathode. So in this case, the anion will move towards the anode to undergo oxidation reaction. Okay, so the reaction here would be the anion. The anion will lose electron depending on the magnitude of its charge from negative to 0. Okay, that is oxidation reaction. This is taking place at the anode. Okay, this is your anode reaction. As the electron is moving from this direction, from the anode, okay, that is through the metal conductor. Okay, the electric current by the generation of electric current to the cathode. Okay, the cation A positive will accept that electron depending on the magnitude of its charge. Okay, reducing its state. Okay. This is from positive to 0. So it is being reduced. Okay, that is the reaction that takes place at the cathode. So if the anion is moving towards the anode, therefore the anode is positively charged. If the cation is moving, this is your cathode reaction. Okay. Therefore, your cathode is negatively charged because unlike sign attract each other. If the positively charged is moving towards this direction, therefore this is negatively charged. If the negatively charged moves towards this direction, this is positively charged. Okay, that explains the difference between the charge of the electrode in an electrolytic cell and the voltaic cell. If you recall, in the voltaic cell, the anode is negatively charged and the cathode is positively charged because it is in the anode where the electron is being expelled from the inner voltaic cell. Here, the ion is attracted towards this. Therefore, this is positively charged and the cation is attracted towards this electrode. Therefore, this is negatively charged. Okay, we have two types of electrolytic cell. We have a passive electrolysis and an active electrolysis. In a passive electrolysis, the electrodes are chemically inert, where they simply provide a path for electrode. And this type of electrolysis is being used in industry, say in the purification of metals that corrodes easily. The other type of electrolytic cell is the active electrolysis, where the electrodes are part of the electrolytic cell. Okay. And this type of electrolysis is used in plating or electroplating. Okay. So, to plate materials to provide resistance to corrosions. Say, in the jewelry industry, electroplating is an example of active electrolysis, where the electrodes are part of the electrolytic reaction. In a passive electrolysis, inert electrodes are used. They are chemically inert, meaning they do not participate in the electrochemical reaction in the electrolytic cell. An example of a chemically inert material for electrode is platinum. Okay, for the first part of our discussion on electrolysis, we have predicting electrode product. In predicting the electrode product, it is not always easy or even possible to predict what products will result when a direct current is passed through an aqueous solution of an electrolyte. In addition to the ions from electrolytes, water molecules and the ions from water, such as hydrogen ion and the OH ion, are likewise present. These may also participate in the electrochemical reaction. Furthermore, the electrode product obtained with a concentrated solution or molten state often differ from those obtained with dilute solutions. In some cases, one or both of the electrodes may react. The anode in the electroplating of valuable metal is one of the reactants, such as gold or silver. To narrow the list of variables, inert electrodes, usually platinum, are used. So the following rules are applied in predicting the electrode product for a considerable number of reactants. Okay, at the inert cathode, a negatively charged cathode in an electrolytic cell, the following occurs. If the metal is below hydrogen activity, electrolysis of the aqueous solution of its salts causes the metal to form at the cathode. For example, if a water solution of cupric chloride, silver nitrate, or of mercuric chloride is electrolyte, it is the copper, silver, and mercury respectively will be formed at the cathode. If the metal is above hydrogen in activity, electrolysis of the aqueous solution of it usually liberates hydrogen gas at the cathode. For example, aqueous solution of sodium chloride, potassium chloride, or magnesium chloride is electrolyzed, hydrogen will be liberated at the cathode in each cases. Why? Because this metal, which has a higher activity with respect to water as the reference, has a greater tendency to undergo oxidation, meaning they have a greater tendency to give electron than to accept with respect to hydrogen. So if hydrogen is present in the form of the aqueous solution in the electrolytic cell, it is the hydrogen gas has a greater tendency, or the hydrogen ion in the aqueous solution has a greater tendency to accept the electron migrating to the cathode. Okay? But if this metal below hydrogen are present in the aqueous solution, it is these metal that are deposited at the cathode because they have a greater tendency to undergo reduction with respect to hydrogen. At the inert anode of an electrolytic cell, which is positively charged, the following occurs. Oxygen is liberated during the electrolysis of most salt, with an anion containing oxygen such as sulfate, nitrate, carbonate, chlorate. Okay. Example for this, we have silver nitrate in water with a direct current, aqueous solution of silver nitrate. Of course, water would be present in the aqueous solution. With direct current, the silver from the silver nitrate will be reduced from positive silver to its elemental state. And the oxygen in water will be oxidized. And we have 4 moles of nitric acid here. The water undergo this reaction at the anode, oxidation reaction at the anode, where the water is oxidized to oxygen and 4 moles of hydrogen ion and giving 4 electrons. Okay, since silver nitrate is very soluble in water, therefore it will undergo ionization. The silver nitrate here will undergo ionization of silver ion and the nitrate ion. Okay, so that is the nitrate from the silver nitrate will combine to the hydrogen from the oxidation of water to oxygen and hydrogen ion. Okay, that is the product. And oxygen is here. This is the overall reaction. And this is how the water is oxidized in the anode. Okay, for an ion such as chloride, bromide, and iodide, but never fluoride because fluorine is the most electronegative element. It has a greater tendency to accept electron than giving off electron. Remember, we are on the anode electrode. We undergo oxidation, meaning you increase your state. So they are more easily oxidized. The chloride, bromide, iodide are easily oxidized than water. Hence, the pre-halogen is liberated, for example, during electrolysis of molten or concentrated sodium chloride. Chlorine is liberated at the anode. In case of dilute solution, oxygen as well as chlorine are formed. The oxygen in the water will also undergo oxidation, and the chloride from the anion of the solute will undergo also oxidation reaction. So let us have a schematic representation of the electrolysis of molten sodium chloride and an aqueous sodium chloride, and let us compare their electrode product. For the electrolyte of a molten sodium chloride, what is present is the sodium ion and the chloride ion. Since at the anode, oxidation reaction takes place, and chlorine is a diatomic, you need 2 ions of chloride, losing 1 electron each, so there would be 2 electron loss total to have a chlorine gas as one of the product, or to have chlorine gas as the product in the anode. Okay. At the cathode terminal, the sodium ion needs 1 electron, positive 1 electron to become a sodium atom. However, there is a total of 2 electrons given off at the anode. So we multiply the equation by 2 to equate the number of electron gain or loss. Okay, so the product at the anode, when your electrolyte is a molten sodium chloride, no water, at the anode is chlorine gas, and at the cathode is the sodium metal. Okay, this is in the aqueous state, meaning they are present in the electrolyte. On the other hand, if you have an aqueous solution of sodium chloride, meaning it is dissolved in water, so we have the sodium ion, the chloride ion, and the hydrogen ion present in water and the oxide. okay, from the OH. Okay, so the anode reaction involved the oxidation of water producing oxygen gas and 4 ions of hydrogen in the aqueous solution and 4 electrodes. Since chlorine ion is also present, it will undergo oxidation reaction from -1 to 0. Here, the oxygen from water, it is +1, -2, from -2 to 0. That is oxidation reaction. Okay. The hydrogen does not change its state here. Okay. Simply ionize here. Now, the chlorine is giving off 2 electrons. So at the anode electrode, there is a total of 6 electrons lost. 4 from water, oxidizing to oxygen, and 2 from chlorine. From 2 chlorides forming chlorine gas. Okay. At the cathode electrode, the reaction is this one. Okay, since hydrogen is present, also a cation present in the electrolyte, because we have an aqueous solution, so hydrogen is present. It is not sodium that will be deposited here, like what happened in the case of molten sodium chloride. Because the presence of hydrogen ion, which is more electronegative or has a greater tendency to be reduced than sodium, if you refer to the activity series, hydrogen is way below here. So, the activity of hydrogen is much lower than sodium. So, sodium has a greater tendency to give electron than to accept electron, and hydrogen has a greater tendency to accept the electron. So, it is the hydrogen ion that is produced during the oxidation of oxygen here that will accept that 6 electrons, forming 3 moles of hydrogen gas. Okay. That is the difference if you have the product would differ if you have a molten state and an aqueous solution of metal that is above in activity with respect to hydrogen. It is hydrogen that is formed at the cathode, not the elemental state of the metal. Okay, let us have an example to furthermore illustrate how to predict the electrode product. So we're asked here to predict what is liberated at each electrode when each of the following electrolyte is electrolyzed between inert electrodes. So the inert electrode here is again the platinum. Okay, so for number 1, we have a molten aluminum chloride, then dilute solution of aluminum chloride, then we have an aqueous solution of magnesium nitrate, and we have aqueous solution of cupric sulfate, and number 5, we have concentrated solution of cupric chloride, and we have a diluted, for the last, we have diluted solution of cupric chloride. We're asked what is the respective cathode product and the anode product given these following electrolytes. Okay, to begin with, let us have the number 1, the molten state of aluminum chloride. So, since it is molten, no water, so the lattice structure or bond between the aluminum and chloride will be broken, and you have aluminum +3 and you have the chloride ion. So at the anode, oxidation reaction must take place. So it is the chloride here. Okay, you have chloride, negative, has to lose 2 electrons to become chlorine gas. Okay. At the cathode, the aluminum will be reduced to its elemental state. So you have aluminum, positive 3, will accept 3 electrons to give you the aluminum solid. Okay, from positive 3 to 0. So your product at the cathode is aluminum. Here, we fill up the table. And for the anode, it is chlorine gas. Okay, for number 2, we have a dilute solution of aluminum chloride. Again, since chloride are very soluble in water, so there would be in water, it will be highly ionized to aluminum positive 3 and chloride. So we have chloride and aluminum positive 3. Okay. Since the word dilute solution, meaning it is dissolved in water, so there would be hydrogen ion and the OH ion, or where the O2, the negative oxygen, is involved. So in the anode compartment, what takes place is the oxidation of water. So 2 moles of water will oxidize to oxygen gas and 4 moles of hydrogen ion and 4 electrons. Okay. Since chloride is present, the chloride ion in the aqueous solution will also oxidize to chlorine gas and giving 2 electrons. So there is a total 6 electrons here that is lost at the anode. At the cathode, we have the cation aluminum positive 3 and hydrogen. Now, referring to your activity series, aluminum is on top of hydrogen. Again, aluminum is more active than hydrogen. It is hydrogen that will be formed or deposited at the cathode, not aluminum, because hydrogen has a greater tendency to accept electron and aluminum has a greater tendency to be oxidized or to lose electron. So we have 6 to get the total, okay, plus 6 electron would give you 3 moles of hydrogen gas. Okay, so to fill up the table, our product, when we have a dilute solution of aluminum chloride, the cathode, we have hydrogen gas, and at the anode, we have chlorine gas and oxygen gas. The oxygen is present at the anode as one of the product because of the presence of water. And it is the water that undergo oxidation to oxygen and hydrogen. Okay? So see the difference? Without water, it is aluminum that is deposited at the cathode and only chlorine gas at the anode. In the presence of water, we have hydrogen gas, not aluminum. And at the anode, we have chlorine gas as well as oxygen gas. Okay, moving on. For number 3, we have aqueous solution of magnesium nitrate. Okay. Here, we have an aqueous solution of magnesium nitrate. Again, water is present. Okay. Nitrate is highly soluble in water, so it will ionize magnesium nitrate in water. Okay. It will be ionized to magnesium, ion positive 2, and nitrate, ion negative 1. So, in the electrolytic bath, the electrolyte will compose of nitrate, negative, and you have the magnesium ion, and the presence of water. Okay? So, it is the water that is undergoing oxidation, producing oxygen. Okay. So, what happened at the anode is you have 2 moles of water will oxidize, producing oxygen gas, 4 ions of hydrogen, and liberating 4 electrons. Okay. The nitrate there will combine with some of the hydrogen. Okay, here. Okay, at the cathode terminal, the presence of water will not reduce the magnesium ion. It is the hydrogen ion, 2 hydrogen ion plus 2 electron will give you hydrogen gas. Again, hydrogen is below activity of magnesium, so it is hydrogen that is deposited at the cathode, not the magnesium. So we fill up the table. In your anode, you have oxygen, and in the cathode, you have hydrogen. The nitrogen is not a product because the nitrates will react with the hydrogen ion, with some of the hydrogen ion in water. Okay. For number 4, we have an aqueous solution of cupric sulfate. Okay. Again, sulfate is highly soluble in water, so the copper sulfate will ionize to copper ion and the sulfate ion, -2. So we have copper ion here and the sulfate ion, -2. And since the word aqueous would mean there would be a presence of water, the hydrogen ion from the oxidation of water, and you will have the oxidation of water will produce here oxygen gas. Okay, so the anode reaction would be the oxidation of water producing oxygen and 4 ions of hydrogen and 4 electrons. Okay. At the cathode, if we refer to the activity series, copper is below hydrogen. It has a greater tendency to accept electron than hydrogen. So the presence of copper being below hydrogen, it is the copper that will reduce. Okay, so we have copper ion +2 plus 2 electron will be reduced to copper solid. So that would be the sulfate will not be reduced to sulfide or to sulfur. The sulfate ion will react with some of the hydrogen in the water, maintaining the pH of the system. Okay, so the product for the aqueous solution of cupric nitrate, at the anode, we have oxygen, although we have here the ions of hydrogen as one of the product of the anode. This will not undergo reduction because copper is less active than hydrogen. It has a more tendency to be reduced than hydrogen. Okay, so the product at the cathode is copper. Okay. Now next we have concentrated, no water. So the ion present is your copper ion +2 and chloride. Okay. So anode undergoing oxidation, we have the chloride will lose 2 electrons. So you have chloride. And no water, no hydrogen will take anyway, and copper is below hydrogen. Even if there's water, it will be the copper ion that will undergo reduction, and you have the copper solid. Okay, so the product at the cathode is copper, at the anode is chlorine gas. Okay, lastly, we have dilute solution of cupric chloride. Okay, let's have the comparison with the product. So the word dilute, there is presence of water. So you have the copper ion positive 2 and the chloride ion as well. However, there would be hydrogen ion and the negative ion of oxygen, okay, from water. Okay, so for every 2 moles of water, it will undergo oxidation, producing oxygen gas, 4 ions of hydrogen, and 4 electrons. Okay, this is negative 2, positive 1. And chlorine is present. Therefore, the chloride will also undergo oxidation. We have chlorine gas plus 2 electrons. Okay. And the cathode, hydrogen is present during, as one of the product for the oxidation of water. However, copper is below hydrogen in the activity series. Again, if we refer to our activity series, the copper is below hydrogen. So it is the copper ion that will receive 2 electrons per atom, producing copper solid. And there are 6, so we have 3 here. So we have 6 here, 2 each. So we have 3 and 3 there. Okay, that would satisfy the 6 electron given during the oxidation of water. So for the table, completing the table, we have copper as the cathode. And here we have chlorine gas and oxygen gas. Okay, that completes the table where we will ask to predict the product based on the activity of the element with respect to one another. Okay. Okay, that's all for predicting the product at the electrode in an electrolytic cell. The second part will talk about the quantitative changes during electrolysis.